All right, to get to the some more of the basics, this is quartz crystal. I like quartz a lot. It's a very fascinating mineral. It is a component of granite and other types of rocks. It's very hard. It has the most hardness of 7. You can scratch glass with it, and glass can't scratch it, depending. Usually if it's just regular glass, it can't be scratched. All right. Crystalline SiO2, that's what quartz is, silicon and oxygen, forms coherent structures, okay? They're called tetrahedrons, meaning silicon is the circle and the oxygen for this example is the closed circle. Has 4 points, 1, 2, 3, 4, and each bond silicon has with the quartz branches out like this to form a tetrahedron, meaning it has 4 corners. And the silicon is in the center. This forms a very, very hard structure. This is why it has the most hardness of 7. Look how ordered that is. Okay? Diamond is similar, but it's different. Okay? Obviously, it's only carbon. But basically, depending on the rate of cooling that this SiO2 occurs, will determine what kind of structure it forms. Now, this would be slow cooling, okay? It takes time to form something like this because they all have to get ordered in the right direction. They have to layer over many, many years, okay? So they just layer out and the crystal gets bigger and bigger and bigger after each successful layer is put on top of it, making a perfect crystal. Everybody's seen those on the on Google or Bing search engines. But if you have that SiO2 cooling really fast, it doesn't have the time to layer. It all clumps together and forms a big mess. It's like glass. There's no real crystalline structure here like there is here, no ordered crystalline structure. That's why when you break glass, it shatters and then you have those surfaces where it bends and it's kind of concave in a way, and then you see ripples in the glass because it breaks completely unevenly in many places. There's a word for that. I have to go ahead and research that to show you guys more about that. But amorphous meaning there's no crystalline structure. It's just all over the place. And that means it cools very fast. Another mineral that cools very fast is olivine. Olivine, not olivine. What's that one crystal like volcanic glass? I think that's olivine. I'm not sure. I think olivine's the like peridot. I'm getting that backwards, but this is like volcanic glass. Volcanic glass is those little round beads that you can find, and if you shine them in light, they look like smoky quartz. They're really beautiful. But those also cool really fast because obviously when lava escapes the surface, depending on the material, it cools instantly with air or with water. There's no time for it to form a crystalline structure like this. This takes many millions of years, depending on how large the crystals are. Another point I wanted to bring across, I didn't want to go over this inside of this talk, but there are bond enthalpies here. I believe the bond enthalpy for a silicon to oxygen bond is around 368 kilojoules per mole, meaning that's how much energy is stored inside of this bond, okay? Now, there's one important thing I wanted to bring up as well as this talk. I'll go ahead and leave this part up so people can look at it. But establishment science, they don't understand that it takes pressure and time to create something like this, okay? They think rocks can form absent pressure in the vacuum of outer space. You don't have to believe me, look it up online. Their accretion models for how planets have formed start with little bits of matter which then clump together for some strange reason to form little conglomerates of stuff, okay? But that isn't how it works, because we have found meteorites that have what are called Thompson structures in them. Now, Thompson structure is also a crystalline structure. A Thompson structure, say we have like a meteorite chunk, okay? If you were to slice out a flat end of it, and obviously, turn it sideways, what you would see, depending on the orientation where the cut was made, you would see these long crystals that kind of zigzag and cross each other, like this. Kind of like that, okay? So you have a slice of it, Thompson structures. There's also another name for it, that big W word. I can't really go over it, but you'll see that word online when you look it up. When they slice the meteorite and they etch it with acid. You'll see these structures. This is crystalline structure in the meteorite. They want you to believe that meteorites are formed from conglomeration, their conglomeration method. And that's one of the things that I wanted to show you with that previous really poorly made low-budget video of the copper slamming into the other copper. Because if that copper bar, there's two copper bars slamming into each other, they can't form this kind of structure. This kind of structure takes incredible amounts of pressure, time, and heat. And all three are not provided via the absence of pressure, heat, and time. Okay? They need pressure, heat, and time. It takes a very long time just to form a tiny little crystal. It takes an incredible amount of heat, plus to form these crystalline structures, that releases an incredible amount of heat. And it also takes a very large amount of pressure to form these meteorites in outer space. That means the only place that meteorites could have formed is inside of ancient stars as they evolve, cool, and shrink. And the material gets deposited in the center of the star, forming the iron crystal core, iron nickel crystal core first. And obviously all the other high ionization material, such as silicon and oxygen, form afterwards, and they form on the top of the star. Given there's already a thick atmosphere that you can't see, that's, during brown dwarf stages and things like that. But hopefully, this sums up a little bit about crystalline structure and what it takes to form it, and the fact that it doesn't just magically appear because of gravitation. You need basic geological concepts to form crystalline structure, and we have evidence of that in the meteorites.